tell us a little bit about that as well as the research plan.
Thank you. It's a pleasure to be here. I graduated from this institution when this building didn't exist, and so it's always a pleasure to be back, especially in the nice new building. So I'm going to talk to you really at a high level about some of the things we're doing at Montana State University, mainly because I knew that it was late on the last day of a long week, and a lot of you are probably pretty tired of seeing a lot of details. So if I don't show you details, it's by design. If you want to know some details, you can ask, and if it's one that I know, I'll answer. So I come to you from Montana State University in Bozeman, Montana. We were just laughing right beforehand about the picture here. I guess I should have said that we do lightsabers in Montana. So what do these things have in common? When I put these pictures together, I was trying to illustrate three things, although now that I look at it, I realize that there are four things illustrated there. So crystal clear mountain streams where you go fly fishing, snow-capped mountains where we can go skiing and hiking, and then this one is intended to show the laser beam, but the fourth thing could also be Subarus. So what do these things have in common? There's lots of them in Montana. And so we draw on that heavily because that's one of the things we have that not everybody has, is a lot of outdoors features. So for those of you who don't know where Montana is, I've drawn it in there to help you. We're up here in the northwestern United States, pretty much due north of Arizona. Bozeman is down here in this corner, just due north of Yellowstone Park. So if you've been to Yellowstone, you've been to our backyard, and you should come just a little bit further north and come on up. We have arguably unbeatable outdoor recreation opportunities, summer and winter. And we also have world-class facilities, something that you may not know about Montana State, since it's not some place that you usually think about with that kind of designation. We are actually a Carnegie R1 university, which means we have the very high research designation. The facilities that we have got a big boost this last year, well, several years ago, by a large donation from a very generous person. And from that donation, then we moved in a year ago to this brand new building. So that's where my optics center is housed now. We had the pleasure of having Jim visit us earlier this year, and it was nice to see that he enjoyed the new building as well. And so I'm going to talk to you about what we do at the university, but this talk will be very heavily flavored by industry, because what we do is heavily influenced by our desire to grow jobs locally and to grow an optics industry. And so you might be saying to yourself, wait a minute, optics industry in Montana? What? It's a thing, and if you don't know it's a thing, this is kind of how it got started. It sort of got started with the invention of the laser in 1960. And the way that is a connection is that this guy, when he was a much younger version of that guy, was working at Union Carbide, and he came into work one day. He's a Montana State University graduate, which is why it's relevant to me and to this talk. This guy came into work one day, and he had a work order on his desk for a ruby crystal with specifications that he had never seen before. And everybody so far had said, no, we can't do that. And the last stop was Ralph's desk. And Ralph said, yeah, sure, I'll give it a try. And so he did whatever he did, and then he tells this great story about hand polishing. The finishing touches were hand polishing. And you don't do that today. And so he made this crystal that, of course, was the crystal that was used by Ted Maiman to make the world's first laser. So Montana State University, in a very indirect way, had a very direct influence on the invention of the laser. And then it took us a while to decide that we were going to do lasers in Montana after that. It certainly didn't start in 1960. But it started in the Big Bang, which in Montana, for the optics people, is 1980. That was when the Big Bang happened, when all of a sudden somebody just decided they're going to create an optics company in Montana. Now, this is a little timeline that I like to show that illustrates the growth of companies. And the reason I like to show this is because we're very proud of it, because this is a very purposeful thing. This doesn't happen by accident. I guess it could, but it doesn't usually. And we set about trying to do this way back here in these days, in the late 1980s, mid 1980s to late 1980s. And I say we in the global sense because it wasn't me. I was studying somewhere else at the time, and I wasn't at Montana State University. But the people that came before me said, gosh, there's a couple startup companies, there were just 2 or 3 of them, and wouldn't it be cool to have some jobs so that all of our graduates don't have to go to Arizona or Rochester or California or somewhere like that? Wouldn't it be great if they could work right here? And so they said, let's get some money to do something together. So they went to the National Science Foundation, got some funds, and started hiring people very purposely, people that had something to offer, not only in just the education and research arena, but in the people that were thinking that industry wasn't a dirty word. And so we gathered a bunch of people. We formed our center in 1995. That's when we were officially recognized by the Board of Regents. But the work to form that center began back in the late 80s. And so we sort of officially became a thing in the mid-90s. And after about 1989, I would say the vast majority of these companies are all direct spin-offs that were very purposely built, with us teaching our students that, hey, if you want a job, you're going to have to go out and create it. And many of them took that challenge and created companies and created their own job. Now we're actually experiencing this interesting thing that some of our students are maybe getting a little lax about that, because they say, well, I don't need to create my own job. We got 40 companies I can work in. And so that's a whole new challenge. And so we're trying to keep fanning the flames of entrepreneurialism and trying to keep this thing going. I'm not going to tell you the story of, that would be a whole nother talk to talk about all the different companies on here, but just to give you a flavor, we have a lot of the early companies were laser manufacturers, just kind of by chance. And so Big Sky Laser, many of you might know them. They don't go by that name anymore. They're now Quantel USA. They make a lot of solid state lasers. ILX Lightwave was bought by Newport, who was bought by whoever is whoever now. But ILX Lightwave was one of the earliest companies, and they don't make lasers, but they make diode laser instrumentation. So any of you that work in a diode laser equipped lab probably have their products on your lab bench. Yes. Yeah. ILX Lightwave was started by Larry Johnson, who's a PhD graduate of optical sciences. And so, yeah, OpSci influence runs deep in Bozeman, Montana. I'm a graduate, and Larry was, and we have a few others running around too. And so just to give you an idea, though, we have these, mostly laser-centric companies for a while. And then it just sort of exploded and became everything. And what you see is, like, Resonon does hyperspectral imagers. If I come to some of these new ones, Blackmore Sensors was founded to chase this holy grail of LiDARs for self-driving cars, autonomous vehicles. That's my graduate students went out and started that company. And I could go on and on, but I don't have time to do that. But you see that we're kind of getting a trend. Somebody asked me at lunch, what's sort of your main theme? And I guess I like to think of our main theme as optical sensing systems, because we do everything from the basic science that can lead to new lasers, that can lead to new laser sensors, that can lead to some solution for somebody's problem. And that's not what everybody does, but I can take pretty much everybody in my center and everybody on this slide here and package them somehow into that sort of theme. And so here's a picture of the people that are primary optics people at the university. We have, it changes depending on how nebulous you want to get with who you count, but we have about 18 tenure track faculty and another half dozen or so research. That's probably 8 or 9 or 10 by now. Actually, we just hired several new ones. And we are we are not organized into a College of Optical Sciences yet, but we are organized in a little bit more conventional departments of physics, chemistry, electrical engineering. But my organization acts as the umbrella that brings us all together and gives us purpose. One of the things I like to say is that we turn grad students into CEOs or CTOs. This slide shows two guys who were, both these pictures on the left show them when they were graduate students giving a talk at a local conference that we do. And then these are pictures of them as leaders of their companies. This particular one down here is kind of exciting because it's just, gosh, what is that, last year or 2 years ago when they were awarded one of these PRISM awards, which is a very high honor for companies. And similar to what Dr. Carney talked about earlier and similar to what happens here at Optical Sciences in Tucson, we don't call it industrial affiliates or something like that, but we have a very purposefully designed annual conference where we put all the students doing optics with all the faculty doing optics with all the companies that we can get together into the same room, put food, put drink, and let good things happen. That's everything I know about growing companies and making the optics center work is to do that. And that's being a little bit facetious, but it's pretty much that simple. You put really smart people in a room and get them talking and great things happen. And then you facilitate some of those things with some other moves. And so this has been a very critical part of our growth, is to have this interaction, especially since we're divided organizationally into different departments. It's really critical that we do this. We bring in people from all over the country and all over the world, for that matter, and have talks so that we can not be hidden away in Montana, not hearing from the rest of the world. We like to hear from the rest of the world. And actually, I just realized there's a couple Arizona people here in these pictures. There's John Reagan, who is an OpSci affiliated faculty. And who else? There's some, oh yeah, this is Peter Smith talking about the Mars mission that he did. And these are just examples of the many, many talks that we've had come through town. And we would welcome you to come too if you want to come and visit with us. So now I'm going to take you through some slides that just talk at a very high level about the kinds of things we're doing in research, because I want to give especially the students some idea of what's there for opportunities, what kind of work exists. And the level of detail will go up and down as my level of awareness and understanding goes up and down. As I said before, we cover the full spectrum from the basic optical science and all the way up to the applications. And I really feel that that's critical, because if you ever stop doing the basic science, then tomorrow's application never appears. So we're always telling the legislature especially that, because they can see that it's important to do applications, but they need some help sometimes understanding that, no, this basic science is where that all starts. So we do some very exciting basic research. Laser crystals, of course, have a long history in Bozeman. What I didn't tell you is Ralph Hutchison, that guy that I told you that polished the first laser crystal, he then went on several years later. His company was doing more and more work with laser crystals, and they didn't want to do that. So they just said, why don't you take your laser crystal stuff and go away and do it somewhere else? So he came home to Montana and started Scientific Materials Corporation. And that's been a fabulously successful company, and to this day still grows some of the world's best laser crystals right there in Bozeman. And then we have some spectroscopy people that are looking at all kinds of things related to the effect of sunlight on genetics. Out of this work comes some tunable lasers and cryogenic systems, just a tremendous amount of variety. We have people doing optical communications. This is actually a recently strengthened area because we did some hiring. And so we have things going on, and this is kind of off of off of this group's webpage talking about the highlights of what they do. They're looking at quasi-single mode fiber, universal multi-mode fiber. This is the latest one that just came about. They're doing some quantum cryptography and optical comm, which is kind of exciting new things. We do an awful lot of work in developing new sensing systems and applying them to problems of interest to us and others. And so we were doing a lot of imaging work, and one day it occurred to me that there's an opportunity that we're just ignoring. We have all of these geeks doing optics, and then we have this huge College of Agriculture. Montana State is a very big agriculture school. Montana is a big agricultural state. And so I called them up and I said, what can we do to help you guys? And they said, I don't know. I said, well, what problems do you have? And they said, well, they started naming problems, and we pretty quickly identified a couple. And I said, well, let's start with two. I want to do that one because it sounds easy, and I want to do that one because it sounds hard. And so we picked an easy one and a hard one. And this is actually an illustration of the hard one, which is taking little compact hyperspectral imagers, flying them on drones over fields, or in the first part of the work, doing it with the imager on a tripod, because going into it from a ground base to an airborne is a big jump. And we're looking at weeds, and you might think, well, weeds, gosh, what's so hard about weeds? This is a really challenging project because what we have is just like in medicine. You might have heard about the problem in medicine that there are resistant varieties of diseases running around. So you treat them with the classic medicine and it just doesn't respond. Weeds are doing the same thing. Weeds are evolving to thumb their nose at herbicides. So you spray a field with herbicide at the tune of a lot of dollars. It can cost millions of dollars per year for farmers, for a group of farmers in a state as large as Montana, to spray their fields. And yet what's happening is now the weeds aren't responding. In other words, they're not dying. When you kill them, they're not dying. And so if you take two weeds and hold them next to each other, you can say they look identical. One is herbicide susceptible, which means it'll die. One is herbicide resistant, which means it will not. And you can't tell by looking at them that one is one and one is the other. But the hyperspectral imager, especially coupled with machine learning algorithms, we've been coupling a lot with computer science colleagues, and it's just knocking it out of the park. We're getting 95+% kind of accuracies. And this is just to show you that we're not always that serious about what we do. And then that led to a new project where we're doing hyperspectral imaging for river ecology. In this case, just looking at a little stream, but in other cases, looking at larger rivers. And actually, Erica, I think you're in that picture. That's good fun. There's also been some exciting work done with microbolometers. Some of you, at least one of you, I know, has fought with this battle. Some years ago, when I was a student here, Bill Wolf, who you guys know who he is, and some of you don't know who he is. Bill Wolf is a famous infrared guy. And I was taking a class from him, and he had a security clearance, and he couldn't tell us what he knew, but he could just tell us, any day now, there's going to be some stuff happening that's going to completely revolutionize the infrared imaging world. And then right after that, they had declassified microbolometer technology that was developed under classified contracts for the military. And that led to these uncooled cameras that eventually, in time, became so small that you could hold them in your hand. Or you can now put them, for a couple $100, you can buy one and slap it on the back of your iPhone and have a thermal camera on your iPhone. That's great. It drove the price of thermal imaging way down, but these are terrible imaging systems. They're spatially non-uniform. They drift like crazy. They're susceptible to drifts with their own temperature. And so up here is just kind of a quick plot that shows the black being the digital numbers that we were measuring, and the red being sort of what we were supposed to be measuring. And then here shows the black body temperature of a source we're looking at, and the red one is the readout from the camera. And so basically we're taking all these drifts and removing them so that now as the scene temperature changes in a systematic way, the readout from the camera does too. We developed these calibration methods so that we could do atmospheric measurements, scientific remote sensing, with cheap, low-cost infrared cameras. The manufacturers told me that we were nuts for trying to do that, but we did it anyway, and it works great. And so it enabled, this was the application we were going after. We were mapping clouds in the atmosphere. But we've also done animals, we've done beehives. Once you have a calibrated camera, you can do all kinds of things. We have folks in the solar physics group that are doing spectral imaging with a heavy computational imaging component. And that all is done on a rocket. So imagine building your little hyperspectral imager and putting it onto a nice optical bench and then launching that optical bench on a rocket. And so it's an exciting few minutes for the students that are working on this project. And they've done multiple launches now. And the reason they do rockets is because this is ultraviolet imaging of the sun, and you can't see through the atmosphere at those wavelengths. So you have to launch it above the atmosphere and then for just a few seconds get data and then go home and process it. I wanted to throw these images in just as a nod to Meredith's talk this morning. She talked to you about polarization imaging, and she was explaining a lot about sky polarization. We've done a lot of the pioneering work in understanding sky polarization. And the approach that we took was with all sky imaging. So these are all sky images, which means the circle is the horizon. So this is degree of polarization on the top and angle of polarization on the bottom at 3 different periods of time. And so a lot of what she was talking about is just illustrated nicely here, but I don't want to take the time to go into all those details. I have colleagues that are doing micro fabrication and nano engineering of structures to achieve very specific polarization response with wavelength response so that we can do finely tuned polarization and spectral control pixel by pixel and create custom imaging systems. This work is done in what's called the Montana Microfabrication Facility, which is a series of clean rooms, and this is enabling all these kinds of things. A lot of work in MEMS, the microelectromechanical systems that somebody else mentioned earlier today, and a lot of biology and microfluidics work is going on here, nanocharacterization, and of course education. There's students that take classes and go into these clean rooms and learn how to do that. And I'll just show a couple examples from my colleagues of the MEMS devices they're making. Somebody was talking about maybe it was you or somebody who was talking about MEMS. I guess it was you, Scott, right? Was talking about using MEMS scanning. That's what this is. So this is 3-dimensional MEMS scanning where you can change the voltage on a little micro mirror and tip and tilt it, but also change a different voltage and change the shape of the mirror so that you can achieve focus control. And from those technologies, they're developing things like this scanning laser microscope with adaptive optics in a scanning laser microscope, or confocal imaging, which is more what you were talking about. And then I have this slide just as a transition that as we develop new materials and new lasers, we find new ways to do different laser sensors. And I just have a couple highlights here. Lots of people are talking about LiDAR these days that didn't used to know anything about LiDAR, and so it's kind of exciting because we've been in the LiDAR game for a long, long time and doing some cool things. This is a little LiDAR system we built to go in a small aircraft like that. This is the back seat of the airplane. You just take the back seat out and put the LiDAR in. And this is actually for mapping invasive lake trout at Yellowstone Lake, which is in Yellowstone Park, just south of us. And then we invented a new kind of LiDAR called wing beat modulation LiDAR, where you shoot out your pulses much faster than you normally do. And from those high sequence of pulses, you can imagine building up at each range gate, you build up a time domain signal, and then you Fourier transform that time domain signal, and you get a frequency. And that frequency, that frequency allows you to distinguish between when you're hitting an insect and hitting a tree or something like that, because the tree is not oscillating, but the insect is because of the wing beat modulation. And so we've pioneered this actually with DoD applications initially, but now we're doing ecological and insect science kinds of applications. I have a lot of field work, a lot of students going out into the field. This is at the Eclipse back in 2017. One of our students that was doing his PhD on that. Here's a team of students looking at a bunch of cameras that we had deployed at that Eclipse. And so the final couple things I'll mention to you is just kind of the technical details of what we have to offer for education programs. We actually that's wrong. It says AS. It's actually an AAS, Associate of Applied Science. But anyway, so we have a 2-year photonics technician degree program that we created strictly because the local industry told us we need this desperately. And I'm sure you guys are hearing the same thing, and you're probably hearing the same thing as well. So we created that. We have a bachelor's program through a minor that can be taken by students in different departments. We have a master's in optics and photonics. And at the moment, we have a PhD optics emphasis in the 3 departments that collaborate. But any day now, you'll see me pop out an optics PhD formally. The classes are always changing, but this is a pretty good list of topics that are taught on a fairly routine basis. So we cover all the optical engineering side of things. There's also the laser physics, quantum optics, nonlinear optics, all those kinds of things as well. One of the things that we do really well that isn't offered in a lot of places is this sort of central topic of remote sensing systems and atmospheric optics. We also have an RU program, so if you're interested in that, you can email me and I'll give you details. And so thank you for listening. I'll just conclude by saying that we have a tremendous variety of things going on that provide opportunities for students and faculty for collaboration. We are just delighted to be part of the optics and photonics community, which, as you've heard throughout the day, is just growing and growing, and there's room for many more of you to join the community. The jobs are plentiful, they're well-paying, and they are exciting, the work that you can do. And the way that your career can evolve in this field, I think, is probably not that different from how it can evolve in other fields, but it's just more interesting to me because I like optics. But you see people doing, like you were saying, Scott, going from theoretical physics to running a business, doing some product development. This is happening every day at Montana State University. We see people going from one side of the spectrum to the other, and it's just really, really fun. And it's very fresh. We have young companies. The students are working hand in hand with people at these companies. We're friendly with them. You'll see them walking the halls of our institution and working in the lab with you day to day. So we invite you to, if you're interested in knowing more, just contact me, and I'll tell you everything else you need to know. So thank you.
Let's see if this plays. The secret is to close. Okay, so I'm Euan McLeod. I'm an assistant professor here. I've been here for about 4.5 years now. And I'm going to talk to you today about some work we're doing on optical trapping of metallic nanoparticles. So this is a little bit of a change of gear. So this is going to be a little bit more research focused than most of the talks you've been seeing have at least some research. This is going to be pretty much all research here. And this is one of the things we do in our group. So the areas in our group are kind of divided amongst these 3 topics here. First, is what I'm going to talk to you today mostly about, is this 3D fabrication using nanofabrication using optical tweezers. And so the idea here is we're wanting to actually build materials in 3 dimensions by picking up individual particles and putting them in places. There's also a component of nanophotonic design, so there's a lot of modeling and numerical simulation for the different sorts of things we want to build here. Let me see if I can get that to go. And then the last is lens-free holographic imaging, and so this is kind of a major component. This might be about half of what we do in my lab by itself. And in this case, what we're trying to do is we're trying to build very small, portable, compact, inexpensive microscopes. And in addition to those advantages, the other main advantage is you can get a really, really big field of view at the same time as very good resolution, basically submicron resolution, but fields of view that are many millimeters by many millimeters. And so we're interested in using this for a variety of different applications, including things like imaging nanoparticles. So almost everything we deal with has nanoparticles involved in some way, and then also biological and environmental sensing. So in order to keep the rest of this talk fairly focused, I'm not going to talk too much about this today, but this is sort of a major thing that we do in my group. So this picture is maybe a couple years old now, but the list of students and the kind of rotation students, there's a visiting faculty member on there too. That's relatively current. What I'm going to be talking about to you today has mostly been done by Jeffrey Melzer and Wei-Lin Liu, who are 2 PhD students in my lab. So I'm first going to start with an introduction of 3D nanofabrication, explain kind of what it is, what's out there already, why it's important. And then I'm going to talk about 2 kind of individual results that we've published in the past couple of years that's on the path toward kind of achieving this. And so one of those is looking at the speed limits of optical tweezers. So you can imagine that if we're going to use optical tweezers to kind of build stuff, we want to be able to do that relatively quickly. So how quickly can we do that? And then another is actually getting more accurate calculations of the polarizability of these nanoparticles. So if you're dealing with the interaction of light with nanoparticles, pretty much the first thing people care about is the polarizability of these particles, which is how strongly do they respond to the electric field of the light. And we've done some modeling to show that there are kind of slightly better ways of calculating that than a lot of people have done in the optical tweezer field recently. So, introduction to 3D nanofabrication. So nanoscale fabrication can enable high-performance photonic devices. And I have a few examples on the slides coming up here. The first is biosensors for identifying and quantifying disease biomarkers. So one of the best-known nanophotonic biosensors, and it's very widely used and used commercially, is surface plasma and resonance sensing. The idea here is you send a laser beam in through a prism. On the edge of this prism, you have a nanoscale metal film, and you look at the reflected light. And it turns out that at a very particular angle, what happens is the light doesn't reflect off of the metal film. It also does not really follow total internal reflection that you might expect with a prism anyway, but it actually couples into a light wave that travels along the metal. So normally you think, how can metal support like the flow of light? So it turns out that at the interface between a metal and a dielectric, in this case the metal and the air, you can form this surface plasma that basically follows along here. And this only works if your metal film is pretty much very thin as nanoscale, because it needs to be thin enough that you get some light that's going to kind of penetrate into it, but it needs to still not be too thick, otherwise you can't really couple into it as well. So how does this work as a sensor? Basically, the angle at which that light couples in is extremely sensitive to the refractive index of whatever's going on the bottom here. And so if you change this from maybe a bare surface to a surface which you just coat with 3 nanometers of water, so a very, very thin layer of water molecules, your angle at which you get this coupling to the surface plasma changes very significantly. And so a lot of times people maybe aren't necessarily interested in sensing water. They might be if they're doing a humidity sensor or something. But let's say you want to sense something biological. What you can do is you can attach things like antibodies that are going to capture a particular type of molecule or a particular biological target. And then when those antibodies capture that target, you've now changed the refractive index in this local environment, and you cause this shift and you measure it. So that's one example. This is another example that we're working on in collaboration with Judy Sue's group here. And so her group works on these micro-toroid optical resonators for sensing. And so she gave a talk on this on Monday for the students if they were here. But one of the areas we're collaborating with is we're trying to improve these by basically adding metallic nanostructures to improve the sensitivity of the devices and then also allow us to couple free space light in by putting these little kind of gold arrays of particles on the side. And so we published a couple of papers looking at kind of theoretical models of how we can improve things there. So the main kind of message for this in the next few slides is that basically these nanoscale features and nanoscale fabrication can be used to improve and make higher performance photonic devices. So here we've taken a microscale device and we've added some nanophotonic features in order to make it better. So other examples include imaging. So Vasily Astratov talked a little bit about this yesterday too, about the idea of using kind of microscale and nanoscale optical elements for super resolution imaging. And so this can be used to image things like material surfaces or subcellular structures. So these are another couple examples from other groups. This is from Sheng Zhang at Berkeley from almost 10 years ago now. The idea is if you build some sort of structure here, in this case it's an alternating layer again of metals and dielectrics, so a lot of interesting optics happens when you mix metals and dielectrics at the subwavelength length scale. What he's built here is he's basically built a super resolution lens. So this is something where the features that he's imaging are basically inscribed into the center of this. You're going to shine light through the top, and then you're going to produce an image at the bottom. And it turns out that the spacing between these different features is below the diffraction limit. So the diffraction limit is how good of a resolution can you get with a conventional microscope. Typically that's about lambda over 2. And so in this case, these are features that are spaced more closely than that. And again, due to the special optical properties of this material that's mixing metals and dielectrics, you can do a better job. There's another example, again, of mixing metals and dielectrics. This is now in kind of a cylindrical geometry, and there are different ways you can do it. You can do it with these different layers, or you can do it with these radial ribs and these sorts of things. Here's another example. So another set of things are photonic crystals and metamaterials. What I showed on the previous slide is an example of a hyperbolic metamaterial. It's this kind of alternating layers of metals and dielectrics. But there are a lot of other types of structures that people have built for these interesting optical properties. So you can start to build things that have a negative index of refraction effectively. So that means that if you shine light into it, the light ray is going to kind of bend backwards the wrong way. You can make things that are circular polarizers. So these are little gold helices. And the idea is when the light interacts with them, they drive the electrons to move around that metal. And these electrons start to move in circles. And that creates kind of a circular polarization. You can create materials that have magnetic properties at optical frequencies. So all natural materials, if you think about the magnetic permeability at optical frequencies, the value of mu, that's 1. But you can start to create these kind of exotic materials by being able to pattern them in 3 dimensions in order to create these interesting properties. So why do people want these properties? They are useful for things like these super resolution imagers that I showed on the previous slide. You can make better optical switches for things like photonic communications applications. An application people have talked about a lot, but again, I think it's in a lot of cases a little bit more hype than actual use of things like optical cloaks. That application starts to make a little bit more sense in radio waves or in radar, essentially. But the idea is you can make devices that are going to bend light around objects in order to hide them. It's all these interesting sort of devices. So how do people make these things? So currently, one of the most common ways of making these interesting nanostructured devices is to do it on 2 dimensions. And so the idea is if you're working with a flat surface, it's a lot easier to build something in a 2-dimensional flat surface than it is in a 3-dimensional system. And so there are good ways of doing that. The 2 most common ways people use are either electron beam lithography. So essentially what that is you put your sample in an electron microscope, and your electron microscope scans its electron beam into a photoresist, and where the electron beam hits, it basically kind of disrupts the photoresist so that when you process it, that washes away, and you get left with structure. So it's kind of like lithography, photolithography, but it's done using an electron microscope. And then the other option here is nano-imprint lithography, which is kind of like stamping or molding. You basically build a stamp or a mold, you squish it into something soft, and it creates some sort of imprint, and that's what you can do. So these are used a lot. This is used a lot in creating metasurfaces, which you can think of as metamaterials, but flat 2D metamaterials. And this would be an application if you want to create very large areas that are kind of even harder to create using electron beam lithography. So these approaches cannot really be easily extended to 3D fabrication. And so that's one of the things we're interested in doing in my group. So 3D fabrication often utilizes additive processes. So the most common ways of doing this right now is something called 2-photon polymerization. So this has been commercialized by a company called Nanoscribe. What they do is they take some sort of photoresist or resin, and they focus a laser down into it, and they scan this little laser point around in the resin, and wherever the laser point hits, the resin hardens. And again, it's kind of like doing lithography, but in 3 dimensions. The difficulty with this is you pretty much have to work with one of these resins that's photopolymerizable, so it's kind of hard to mix in multiple materials. You can take your structure at the end and coat it with metal, but you can't build multiple materials together from the ground up. And then the other difficult thing is, again, there's a little bit of a resolution limit, so it's kind of limited to about 150 nanometers, 160 nanometers laterally, and about 300 nanometers vertically. Another approach is self-assembly. So you can rely on chemistry or biochemistry to basically stick things together by coating them with different types of chemicals that are going to adhere, and you can kind of build these sort of structures that are maybe arrays of different types of nanoparticles, but it's hard to build complex structures out of that. And then the last area is optical forces, which is really what we're going to look at. And so the current challenge in this field is that the assembly of heterogeneous materials with sub-100 nanometer resolution in complex 3D geometries is still kind of a pretty major challenge. And so we're developing an optical tweezer platform to basically overcome this challenge. So I've been talking about optical tweezers a lot. Optical tweezers just won the Nobel Prize in Physics last year, and they were invented in kind of the 70s and 80s, when those main papers were published, and Art Ashkin was the kind of principal author on that, but he just won the Nobel Prize recently. So the way this works is basically based on momentum conservation. So if you send in photons, even though they don't have mass, they carry momentum, and their momentum is Planck's constant divided by the wavelength of the photon. And so let's say that we have some sort of particle. So in this case, we're going to work with a microscale particle, where we can do more or less a ray trace, and we have a laser beam, and the laser beam is going from left to right. The optical axis here is the z-axis, and so as you move away from the axis of the laser beam, the beam intensity kind of degrades a little bit, and our particle we've positioned off axis, so it's not right where the laser beam is going. You have light rays coming from your laser beam. This is going to act a little bit like a lens, so these light rays are going to refract when they hit this surface. And now every time the light ray refracts, you've changed the direction of the photon, which means you've changed momentum. And so Newton's laws tell us anytime you have a change in momentum, there must be a force associated with that. So the idea is this light has been refracted by the sphere, and it's changed the direction of light, and that means that the light must have exerted a force on the sphere. This light ray here came from a more intense part of the beam, so its forces are stronger than this light ray, which came from a fairly weak part of the beam. And so if you add all these forces together, you end up with two types of forces. Basically a gradient force that's going to pull this particle to the optical axis, and then you're going to end up with a radiation pressure force that's pretty much going to push this particle downstream, kind of far down. And so this is what people use for optical tweezers. If you want to create a three-dimensional trap, you somehow have to deal with this radiation pressure force. One way you can do that is you can take a laser beam and focus it down to a very, very small spot, in which case you end up with a gradient force that actually pulls you back toward the focus in Z and can be stronger than the radiation pressure force. So that's the idea of how optical tweezers work for microscale particles. For nanoscale particles, you end up with these same sort of forces. The picture that I like to think of there is the kind of static electricity picture. So let's say you take a balloon and you charge it up. Somehow you rub it and you hold it next to your hair. Your hair is going to stand up. And the reason why that happens is you've charged the balloon. The balloon is then going to induce some sort of polarization on your hair, and it's going to bring your hair up. So the same sort of thing happens with a laser and a nanoparticle. The laser has an oscillating electric field. It's going to induce a polarization on your nanoparticle, and that's going to cause an attractive force, pretty much. But you end up with the same sort of result here. So we can use this to trap a particle at the focus of a laser beam. So this is our kind of an example of this system, which let me go back and it should play here, which has one of my PhD students basically spent a long time kind of developing this system. So what we have going on here in the middle here, this is kind of a map of our system. This is a microfluidic chip, and this microfluidic chip has these 4 ports. And in these different ports, basically we're going to use 3 of them, we inject different types of particles. And so one of the things we're interested in doing is we're interested in building these 3D structures that are composed of multiple different types of materials in parallel. And so we have sources for each one of these different types of materials. So it might be, a metal nanoparticle, a dielectric nanoparticle, and maybe some sort of microscale particle. And so what we can do is we can use our optical tweezer to basically go to one of these inlet ports, grab a particle, bring it back into the central region, which is where we're going to assemble things. And when we do that, we then start to stick them down to the surface. So what's involved here is there's a lot of chemistry involved to kind of coat particles with different types of chemicals such that they'll stick to the surface initially and then stick to each other as we start to build things up. And so there's a little bit of a diagram of starting to build an array of particles where you go, grab one, bring it back. And there's a lot of kind of feedback mechanisms involved to make sure that we achieve and maintain high positioning accuracy. So this is done on kind of a vibration isolation table, and a lot of effort involved in trying to make this. What we're trying to do is we're trying to move from a system where we can position as kind of a small handful of particles to something where we can position thousands of particles in a fairly rapid method and rapid way. Okay. So I'll stop there. So these are another couple examples of just kind of, again, what I said, small assemblies of handfuls of particles here, where we can kind of position things like individual microscale particles. We can position nanoscale particles, different types of particles here. Some have been doped with fluorescent dye, and some are not doped with fluorescent dye, and we can kind of build these things up in 3 dimensions. Okay, so as I said, we're trying to basically go from this platform where we can do this with maybe a couple particles to something where we can scale it up with to a very large scale. And so one of the things we're interested in is if we want to build something, we want this to happen in a reasonable amount of time. We can't have a PhD student there sitting there for a whole year as they go grab a particle and bring it back. And if each one takes 1 hour to position, it's never going to be able to build something in a reasonable amount of time. So one of the things we've looked at is what are the fundamental limits for being able to do this. So there are a few other people who have looked at this sort of problem before. Typically, though, they've worked with microscale particles, and their speeds are on the order of a few tens of microns per second in this case. And so we're interested in how does this translate for nanoscale particles, and can we go faster than these other people here? So what we've done is we've done some experiments where we basically just grab a particle, we manipulate it at high speed, we then hold it at constant speed, and then we're going to decelerate it down, and we're just going to see whether or not the particle stays in the trap. And we basically do this many, many times for different particles, different laser powers, different manipulation speeds. And so what happens is we look at the balance between the optical trapping force, which is mainly this gradient force that we care about, and we look at the drag force from the liquid. So we're doing all of this in water, and so we're dragging this particle through water. So eventually that drag force becomes stronger than our optical tweezer force, and we might lose the particle. And so we're looking for basically that balance. So these are the results of how fast can we drag a particular size of particle. So these are different particle diameters as a function of the power in our laser beam, and this shows us the fastest speed we can drive. So essentially, as we go to higher laser powers, we can drag our particles more quickly because we exert a stronger optical trapping force on them. And then we can also do this for a variety of different particle sizes. So these look at kind of different diameters of polystyrene. And then we can also do it for nanoparticles. So here we've done silver, we've done gold, we've done polystyrene. So we can take basically the slopes of the curves on the previous graph. So these are the slopes, and we can plot them again as a function of particle diameter, and we have a fairly good understanding of how those slopes of those curves scale for different particle sizes. There's a little bit of some scaling factor that I won't necessarily go into there, and a little bit of theory that I don't need to go into here either. But we have a fairly good functional agreement between the theory and experiment for a range of particle sizes and materials. So one of the interesting things is we want to be able to do this as fast as we can. So what I showed you before is that as we increase the trap power, we can move our particles faster and faster, and that means we can potentially build things faster and faster. But eventually you reach some sort of problem, because as you turn up your laser power too high, you notice that these things that used to be straight lines are now starting to roll off a little bit, and then they end. And so the question is, what's causing this? And we're pretty sure it's something thermal, and we think that it has to do with we're heating these particles up so much that they're getting close to the vaporization temperature of water. So we're starting to form kind of small little vapor bubbles at the surface of our particle, and that's destabilizing our trap. So for nanoparticles, stable trapping disappears at power levels about 150 to 250 milliwatts, and that's kind of just what I said out there. So that's this our limit here in terms of power. And then for the microparticles, we're really limited by the technology of our stage in this case. The stage we're using is a piezo stage that takes these individual little steps, and if you drive it at really high speeds, it starts to vibrate. You can actually hear it buzzing, and we think that that's what's causing this kind of upper limit up here that we're kind of encountering in that case. So we've done some modeling, too, to kind of understand, again, what role the temperature plays. And again, we need to be our laser power needs to be turned up high enough that we can form this stable trap. And so that ends us up being, we need to be above this white dashed line. But if we get too hot, we start to reach this vaporization temperature of water, and that's going to cause problems. So we want to kind of operate in this region here. So we can calculate heating based on the absorption cross-section of the nanoparticle. We think it's dominated by absorption in the particle, not the surrounding liquid. This, again, there's one scaling factor that's we've kind of applied to all our data to account for kind of laser power loss in optical elements in our optical system. And one interesting thing also is that despite the high speed here, cooling is dominated by conduction, not advection. So a lot of times if you think of, like, let's say you hold your hand out the window of a car, your hand starts to feel cold, and that's because the blowing wind is cooling things down. and it's different than if your hand was just held stationary in a car out the window. It would not be so cold. But in this case, the size scales of the particles make things very different, and the cooling is the same whether the particle is trapped or whether it's moving. So basically, it's not moving fast enough to be cooled by advection, which is a little bit surprising. Okay. So where do we lie in terms of these previous results? So up here, these are the optical tweezers results that I just showed you. So we can kind of go in this 160 to 220 microns per second. So these are some of the fastest speeds for any size of particle. And in particular for nanoparticles, they're some of the fastest speeds. If you compare this to that 2-photon polymerization method, which I think would be kind of the closest thing we're trying to compare to, which is Nanoscribe, is that commercial company that does that here. We're about the same sort of speed in terms of their piezo system. So they have two systems. They have a galvo scanner system. They have a piezo system. Piezo system is a similar sort of speed. It's a little bit different because they write a continuous line, whereas we have to go grab a particle and bring it back. So in that sense, we would definitely be slower. But where we can kind of do a little bit better job, I think, is in terms of resolution, ultimately, and then also in terms of the ability to mix multiple different types of materials together. But in any case, these are particularly high nanoparticle optical trapping speeds, and we think they can be competitive for nanofabrication. So I don't have too much time to go over this. I might just show kind of the introduction here and the main result and skip over a lot of this. So one of the things we noticed when we were doing this is if we're trying to match the forces and match our experiments to models, this force depends on something called the particle polarizability, which is this alpha here. And that particle polarizability, there's basically a real part and an imaginary part, and that determines how strongly does the light interact with the optical tweezer. So a lot of people in the optical tweezer community, this seems to be a little bit restricted to optical tweezer community, have kind of relied on an equation proposed in this paper. So this paper was basically the very first paper where they optically trapped metallic particles. This was back in 1994. And this is a fairly standard equation for polarizability, something called the Clausius-Mossotti equation. And basically they say that this is valid when the skin depth obeys delta much greater than the particle radius. So the skin depth is how much does electromagnetic light penetrate into a metal. So normally for most metals that skin depth is about 20 nanometers, 20, 30 nanometers. So what they're saying is if your particle is bigger than about 20 or 30 nanometers, you can't use this equation, and instead you have to use an effective volume equation where you, rather than taking the full volume of the nanoparticle to determine the polarizability, you only take the volume of a thin shell equal to the skin depth. And so a lot of people have used this, but what we found is that actually that original equation, the original Clausius-Mossotti equation, actually works significantly better. And the reason is these particle permittivities are actually complex. And so the complex part of the permittivity really already accounts for that skin depth and that skin depth loss. So this is a picture again. If you have a really small nanoparticle, even if it's metal, the electromagnetic field penetrates into that metal because this diameter is kind of on the order of the skin depth. However, if you have the diameter that's much larger than the skin depth, you only get electromagnetic fields around the outside. Okay. So we've kind of compared in theory, these dipole models of polarizability to Mie scattering models. And the Mie scattering models are more rigorous and more accurate, and they don't really have this question of whether or not there's a basically they don't rely on a polarizability, so they're going to be more accurate. And so what we've basically shown here is that for models that involve the skin depth correction, which is the blue and purple here, you have errors that are much, much greater over a variety of particle sizes than models that do not involve that skin depth correction. So there are a few other corrections. There's one called radiation reaction, which is the difference between the yellow and the green. That doesn't play a huge role until you're about 100 nanometers. So here, basically, this is telling us that we could treat these particles like individual dipoles up to about 1/10 the wavelength, lambda, which is about 100 nanometers in this case, and that it's much better to use this kind of full volume approach than this effective volume approach that people have been mostly using for kind of a long time in the past few years. Okay, so we looked at this with optical tweezer forces as well, and again, it works better when you use the full volume. And I think I'll skip over the rest of this and just end the summary here. So we're interested in trying to use nanoparticles to kind of build interesting 3D materials, 3D photonic devices, and test those and kind of make it into a rapid prototyping system. We've looked at a few cases as to how quickly do we think we can ultimately position these particles. And then we've also done some work on trying to improve our modeling and of how strong the optical forces are and how these particles scatter light. And I would be happy to take any quick questions now, too. And then after this, we have a break coming up. Yeah, go ahead. So basically what I've shown you, so it's really small handfuls of particles, but a lot of the work is there to build basically a larger device. It's just, it's one of these things where something works, 9 out of 10 times, but that means if you want to try to do 10 particles, something breaks. And so we're just kind of debugging those small things left. So it's kind of small.